Hi everyone, welcome to our first session, the Deep Learning Revolution. Today, we will cover a brief history of machine learning, look at what deep learning really is, and explore its impact on some groundbreaking applications. In this session, we are going to learn about fundamental mathematical concepts as a core in deep learning and such examples of deep learning implementations. First, on the outline today, we are going to brief history of machine learning. And the second, we are going to learn how the deep learning impact our daily life. Section 1. A brief history of machine learning. Let's rewind a bit. Machine learning started with simple algorithms, basically systems that learn from data instead of following rules. The early days were about decision trees, linear models, and support function machines. The big breakthrough came when researchers realized that we could build systems inspired by the human brain. This was the birth of neural networks. But here's the catch. Back then, we didn't have the computing power or enough data to make neural networks truly effective. But that all changed around 2010s with faster GPUs and way more data. Suddenly, we enter the deep learning era where neural networks become deep, meaning they have many layers, not just one or two, because they need to process more complex information. So, what is deep learning? Deep learning is a type of algorithm inspired by how human and mammalian brains process information. It's based on neural networks, which are now the foundation of deep learning. Because machine learning proven effective in real-world machine learning applications. Let's get a bit biological. The brain's basic processing units are called neurons. Neurons sense electrical impulses along axons and synapses, which connect to other neurons at the synapses. Chemical signals called neurotransmitters can stimulate or inhibit whether the next neurons fire. The human brain itself has about 90 billion neurons and 100 trillion synapses. Neurons fire if they get enough stimulation. The strength of these synapses determines how much one neuron can influence another neuron. Learning in the brain actually means changing the strength of its connections. These brain properties are captured in simple mathematical models called artificial neural networks. This approach started way back in 1943 with McCulloch and Pitts. In deep learning, we have artificial neurons which can be described mathematically. This can be expressed in mathematical form of wait times. Input neuron times will be a new input for the next neuron. Here's a quick background. First, we have inputs. These are like the activities of other neurons connected to this neuron. Weights are the continuous variable that represent how strong each connection is per neuron. Pre-activation is a calculated value based on inputs and its weights. And lastly, we have activation function and output activation. Activation function is a nonlinear function applied to the pre-activation neuron, basically to change the nonlinear function to linear function. And lastly, we have output or activation. This is the neuron's final output. After applying the activation function, it will change to a specific output. Okay, now we are going to learn about how deep learning impacts our daily life. This is a research in deep learning. First, we have medical diagnosis. Look at skin lesions. Malignant melanomas versus benign nevi, distinguish is very impossible for the untrained eye. Writing a manual algorithm for this task is basically impossible. But deep learning using neural networks can learn to predict labels directly from image. In fact, deep learning has achieved a level of accuracy that exceeds a professional dermatologist. Second, we have protein structure prediction. Proteins are the building blocks of life, made of amino acid chain folded into complex 3D shapes. Predicting these shapes from the amino acid sequence was a fundamental open problem in biology for decades. Measuring them in the lab takes a long time, but now deep learning can take a sequence and predict its 3D structure. For example, AlphaFold is a great example. Its predictions are often as good as experimental ground truth. This is called supervised learning, application with major implication for biology and drug discovery. And lastly, we have synthetic data generation. Here, the training data is just a bunch of sample image. The network's job is to create a new image with the same type. This is called unsupervised learning because the images are unlabeled, unlike the previous cases that use labeled data. And we have large language models. This is one of the research that building powerful model from processing your natural language in advance in machine learning recently. Large language model use deep learning to create rich internal representations that capture the meaning of language. They can generate text, just like what you're hearing now, by predicting the next word in a sequence. They train using self-supervised learning. They extract input-output pairs from fast text dataset automatically using transformer, so no human labeling is needed. Because they are using like very large training sets and very large networks. These models are starting to show capabilities that look like early signs of artificial general intelligence. So that's the deep learning revolution in a nutshell. We've gone from simple algorithm to powerful deep learning models that impact everything, from medicine to a language. And this is just the beginning. There's so much more to come. If you're eager to learn more about deep learning, we still have many sessions to talk about. References took from here.